Good morning, good afternoon, good evening, everyone, depending on where you're attending this from. Welcome to the first talk in this CryoSCOPE monthly webinar series, where we will showcase scientific advances from our project. My name is Harsh Beria. I'm a research scientist at ETH Zurich in Switzerland and the scientific coordinator of the CryoSCOPE project. Today, with the help of Mariam Yunus from Revolve, who will be helping we moderate the meeting. We'll be hosting the first monthly webinar. CryoSCOPE is a Horizon Europe research and innovation action aimed at understanding physical and chemical processes within the coupled cryosphere, atmosphere, hydrosphere system across cold regions in Europe and India. The project brings together 20 partners across 9 countries and is co-funded by the European Union, the Swiss State Secretariat for Education, Research and Innovation, and the Indian Ministry of Earth Sciences with a total budget of approximately 10 million euros. I have the pleasure of introducing today's speaker, who is Dr. Thomas Swinger. Thomas did his diploma in engineering physics and a PhD in mechanical engineering, both from TU Vienna. Since 2001, Thomas has been working at CSC in Finland. He is very well known in ice sheet modeling community, having developed the state-of-the-art ice sheet code Elmer Ice. Thomas has also co-authored more than 60 publications and is also an adjunct professor in physics of the cryosphere at University of Helsinki since 2013. Today, Thomas will be presenting his latest cryoscope work titled Using Coupled Models for a Better Understanding of Glacier Hydrology Processes. The talk would be about 40 to 45 minutes, and we'll have 15 to 20 minutes of Q&A, question and answers. You can insert your questions in chat or raise your hands and we'll take it together. Without further ado, I would now hand over the stage to Thomas.
This is, of course, never in my case work done by myself alone. There is a contribution from quite a few people here. I underscored those that are actively working in CryoSCOPE, and particularly want to mention Nikola Jovanovic, because he is doing the heavy lifting on the glacial lake outburst flood, machine learning part, of which I took a lot of slides from him. Right, with no further ado, I will go to the objectives. So what are we doing inside CryoSCOPE that links to the work I'm presenting today? So we have two main topics: improving the assessment of potential glacial lake outburst floods, aka GLOFs, and understanding the changes in impacts in subglacial hydrology by glacier retreat in Svalbard. I will go into details what in particular is of interest there. So the first one is a cooperation between mainly CSC and FAU in Erlangen. But we also have a cooperation with NTNU where we do process modeling of a single glacier, but this is not part of this talk today because this has just started to be undertaken. The second part is a cooperation between CSC and UNIS in Svalbard, namely with Andy Hudson. Okay, for the first objective. So we have records of active or of GLOF events, so glacier outburst floods events, some statistics. We are mainly interested in CryoSCOPE in 3 areas, which here are underlined with bold letters. So the European Alps, Scandinavia in particular, mainland Norway to be precise, and Central Asia, very important because we think that a lot of potential glacial lake outburst floods are not really even recognized there. And there is the strong link to the cooperation with our colleagues from India in this project. Why is it important? So the rate of glacier thinning has vastly increased during the 20 years and it will not stop, which means that the glaciers retreats, glacier retreat and potentially uncover over deepenings that, if the hydrology plays with it, can become lakes that can, in some cases, be dammed by unstable features like moraines or some rest ice that is lying around. Be aware that the picture to the right just shows a proglacial lake, but without any danger, because this is Basterz in Austria, glacier very close to where I come from. I just had this picture at hand. So these lakes then can drain catastrophically, causing so-called glacial lake outburst floods. And we want to know the potential existence also in the future of those lakes that can lead to these catastrophic events. Frequency of those is predicted to increase simply because of climate change, which is a fact. So we need to be able on a large scale and a large time span to model the timings and the locations of such glacial lakes that can lead to these catastrophic events. And that brings us to the method of machine learning, because doing it with a process model for each and every glacier is currently out of the question and actually not sought. So the idea is to use the process model. This will be Elma Ice, and we'll explain it later, and produce the data for training a machine learning model that then can be deployed and used for these vast temporal and spatial scales. For the second topic, why are we interested in the changes of subglacial and even groundwater flow changes in Svalbard? There is, and this has been reported, I think, even in the Nature paper, there is the fact that we have a vast retreat of glaciers, mainly on land in this case, in Svalbard, that if the timing is right, can be such that they enable openings in the usually closed permafrost, which existed after the Little Ice Age, meaning that the high pressure groundwater finds a way to make it to the surface. And if there is thermogenic gas storage in between these new paths that the groundwater can take, it can lead to the uptake of those gases, mainly methane, and we have outgassing in front of these glaciers. And to get some idea on the amount of these contributions in originally safely stored methane, we want that would be helpful, because we think also that there might be areas around Greenland that could have similar effects, and we know that Greenland is quite something bigger than Svalbard. So these are the main motivations here. Here a picture of these upwelling water streams. I don't know, can you see my, maybe I changed to better pointer. Here we go. It's a pointer. So if you hopefully can see it on the screen, here in the front of the glacier, you have these upwelling waters that in this case apparently froze over during the night, I guess. But these funny structures can be seen in many places in Svalbard, and they indicate that groundwater can make it to the surface in front of glaciers. I make a short break. Is there anything in the Q&A, or does someone have questions about these objectives at the moment?
Uh, if if you have a question, you can either raise your hand or put your question in chat. So far, we do not have any question, Thomas.
That's
In
fine,
chat.
then I continue.
Thanks.
Going to the tool for the job in this case, as Harsh already mentioned, I'm into ELMA ice development here at CSC at my institute. Shortly, ELMA ice is a 3D computational glaciology code, so usually known as full Stokes, or we can do the 3D Stokes equations, also some approximations. It runs on supercomputers, so we can do large scale runs like here on the right-hand side. Yeah, it is, I think, in the literature quite well known. We have, I think, at the moment 36 peer-reviewed publications. If you want to know more, you can check it out on elmaice.elmafem.org. We use three components of ELMA. One is the ice sheet or the glacier code. It's one and the same. That can also, of course, be run on steep, narrow glaciers of Svalbard, for instance, or in Central Asia. We have recently developed, okay, 21 recently or not, but we have developed a geothermal groundwater model that actually was in the context of nuclear waste repository storage, the evaluation of the permafrost of the one that is actually being taken into use quite soon here in Finland. So this is a product we have there, so we can compute groundwater and permafrost. And we have in glaciology, quite well established glacier drainage system, GLADS, also implemented in ELMA here. A example, if I could trigger the whole thing. Yeah, here we go, of the evolution of the drainage system in terms of channels and watershed underneath Pine Island glacier regions in Antarctica. So these are the three components we are using. Generally, if we look at the ice flow model that somehow can produce a water source, or the water source is given by the intake of at Moulins, we have the geothermal groundwater model here, which itself consists actually of four different submodels, but the main ones are the heat transfer. That also includes phase change, of course, so we can freeze the water, we can thaw it, and the groundwater transport. But there would also be the option, not taken into account here, but in general, of bedrock deformation, which is in no context to glacial isostasy, but rather the rock skeleton acting or reacting to the increased or decreased pore pressure, and solute transport, which is important, for instance, if you are close to an ocean and can have salt intrusions into the water body that then, of course, vastly can change the melting point. Generally, it is not a good idea to directly throw the water source, in particular if you have it from Moulins, into the groundwater model, because it will completely overwhelm it. So you need something in between, and that can be achieved by putting a subglacial hydrological model, which I already introduced by GLADS, in between that then computes a water pressure, and we have a pressure-driven groundwater system. That's usually the setup we are using here. If, of course, we are just interested in getting the GLOFs or the existence of proglacial lakes for the future, we are not interested in the permafrost underneath. So then we just use the system between the ice flow model and the subglacial hydrological model. But those cases basically have those components and their particular usage in common. How does this look then on the glacier level? Here, the glacier will present in quite a few minutes. So we have the ice body above. So we solve for temperature as well as the velocity of the ice. And that, of course, if we are in a transient mode, also the evolution of the free surface. So mainly this means glacier retreat. We have the two-dimensional layer of the subglacial hydrological system underneath. And then if we are interested in the evolution of the permafrost, we have a groundwater permafrost system and even underneath that can even consist out of multiple layers of different hydrological conductivities. In the case of the nuclear repository I showed before, actually we were defining the material element per element. So if one has a very high resolved geological structure or data, we can even do it on that level.
I
Then
also see a question in chat from Takis, which is it possible to run with GLADS for the whole of Greenland, and how does the simulation take?
um, I presume since it has been done for the Amundsen Sea sector, yes, it generally depends on how long you want to run it and what the size of the computer is you have in your basement or you log into. So I think in principle there is no obstacle, but of course the issues usually lie in the details. But so Amundsen Sea sector has been done. It was not easy. I think it has been done in cooperation actually with Mauro Werder from ETH. There was a student visiting him. So it, in principle, yes, but not easy.
Okay.
And for Saurav, maybe you keep your ask your question by writing, and we take it after in the
So
end.
Saurav now put the question on chat, and I'll quickly take it and before we move on. Is there any plan to calibrate the subglacier model? And if so, then how?
To the point, yes. So I guess it was GLADS.
Hmm?
Their calibration, there is a intercomparison between subglacial models. It's called SMIP, where there was a basically, yeah, as I said, intercomparison. That doesn't really help for calibration. I personally have not planned. I guess one could try to do it if one has a real good measurement of both the runoff exactly position where it is being added to the glacier bedrock and then what comes out of the glacier snout. And then maybe one could do some calibration. Else it's pretty difficult to get all the parameters set in GLADS. So this is, yeah, a very, very good question and maybe something I personally don't really can answer. It would need a field glaciologist to give the answers if we have all the data to really calibrate them.
Thanks, Thomas. And quickly, there was also a note from Nicola, and I read the note. Thomas, there's a correction. The training data does not pertain directly to GLOFs, rather to a subglacial hydrology emulator that would be then coupled with IGM in this case. That's a short note.
Yes, I'm coming to that. Sorry. Yes, sorry, Nicola. Yeah.
Thanks, Thomas.
Okay, then I continue. So for the data training, data selection, and good that we have Nicola here, so he can then perhaps take questions I am not able to answer because it's his work. So Elma ice is used in terms of GLADS to train an emulator for the subglacial hydrology. Actually, if we, I think, are completely precise for the hydropotential part of GLADS. So, but for the application, in order to be able to cover with the emulator or the machine learning model, actually, I was told is the better wording for it. A few glaciers have been selected and a process model, in this case GLADS with Elma Ice, is run on it. We have 70 glaciers, so 20 from Svalbard and Scandinavia, 20 from the Alps, and 30 from Central Asia. They have been selected by certain criteria that they cover all possible types of glaciers in terms of area, slope, aspect ratio, elevation, etc. We then use downscaled daily climate for both temperature and precipitation, and a degree day model that then computes the accumulation and the ablation, and particularly the runoff. I guess is the most important thing here, that we really know what the contribution of the water is going into the glaciers, which is assumed to be completely transferred to the bedrock. So there is no surface runoff accounted for here. There is a special model or method of how to distribute the intake of the water into assumed moulins on the glacier surface. This is explained in Werder et al. 2013, which is also applied here. So in the end, what one gets is also by scaling with different climate scenarios and introducing some stochastic element by noise. A lot of simulations are being run using GLADs in Elma ice, and this is then done within the project on the CSC Euro HPC facility Lumi, which is nice. So basically we at CSC have control over the installation on this machine. So we have Elma there and people can run, and there are also GPUs that then can be used for training. Okay, so and here I'm a little bit walking on thin ice because I'm not involved at all in the training side. This is completely on Nicola's side. So Nicola might jump in if I'm talking nonsense here. So incorporating physics, so physics-informed systems into the loss function, for instance, the Darcy-Weisbach law. The potential limitations are the structured grid and also would be periodic boundary conditions, but fortunately glaciers are not periodic, so this should not be an issue here. The inputs into the model are the ice thickness, the pad topography, surface melt input, molar locations, the basal velocity, and the ice mass, parts of it, of course, coming from Elma. The output would be the hydropotential, and of course then in a derivation of it, the subglacial discharge. And with this emulator, then we try to cover the whole area, which has not been done yet. I think this is work in progress as we speak, of the Alps, the Norwegian mainland mountains, and Central Asia area, particular the Indian Himalayas and Karakoram.
Hi, Thomas. I was just thinking like the Moulin input. So that's kind of a continuous input. Also, like you cannot just simulate like a drainage of a moulin, or is it like the input, is it like happening continuously? Or can you say, okay, now we have a drainage event at this moulin and all the water flows in instantly or like very fast?
Okay, so maybe I didn't explain it. So we have daily climate. So we have on a daily basis the precipitation and the temperature, and from the degree day model we have a runoff in this resolution. So basically the input into the molars is based on that, and of course the surface slope, etc. So you get a daily signal of a recharge of the subglacial system by the molars. Is this satisfying answer?
Yeah. So, but like then it's like kind of a continuous flow, like you
continuous on that time resolution, yes.
And
but if there is of course no runoff, there will be no water supply to the system.
But can you also do like make an experiment that you say, okay, we have this filled moulin and it will drain in half a day?
Okay, you mean some kind of capacity within? the molar.
Yeah,
So you fill it with water, and the outlet is then kind of a delay.
yeah, like that,
Yeah,
like really.
there is a parameter. It's called, what was it? Molar volume or area, where you can kind of mimic that. I have not played with it, and generally
Hmm.
in our applications we basically hit the system with what is coming in. So it's
Hmm.
input equals output, but you can there's a way in GLADS to kind of have a storage capacity, so to say, within the
Hmm.
molars. Yeah,
Okay, thank you.
haven't tried.
Yep.
Okay,
Thanks, Daniel.
then
I
I
think we can
continue.
maybe continue. Yeah. Thanks.
How am I doing time-wise? I'm
I think you're doing quite well. We have
yeah.
about 17, 18 minutes more.
Oh, plenty of okay. Because now I'm entering my comfort zone. So the stuff that I mainly drive in modeling. So this is stuff done heavily by Nicola and Samuel in FAU in Erlangen, what I showed before. This is now in my cooperation mainly with Andy Hodson in UNIS Svalbard. So as a test balloon, and there is no methane expected underneath Midre Lovenbrain, but simply by the fact that Midre Lovenbrain is one of the best monitored glaciers on the planet, mainly I think due to the fact that it's a 2 minute scooter drive from the New Orleans station here at Svalbard. We chose this glacier to try out our fully coupled model. So it's basically a test case where we want to show that the method works. Later, we want to turn to other glacier. It's the Scott Turner Brain, which is very close to Longyearbyen, which will is part of heavy field campaign at the moment, and we will apply all these methods to this glacier. So that is basically the CryoSCOPE site then of investigation. But this was a kind of a test case for establishing the numerical methods that we are using in the fully coupled thing. This is, by the way, in large parts, a presentation I will give in 1 week in EGU, but go there too because I have additional stuff there on the temporal evolution of the glacier from 1936 to present. Anyways, the glacier is well known. Its even thermal structure has been investigated before, also with contribution from myself. It is in heavy retreat, like almost every Svalbard glacier that is not currently searching. And yeah, so it's a perfect candidate for testing the interaction between a glacier retreat and the adjacent permafrost groundwater system. We have a vast amount of data what comes to surface runoff. We have DEMs reaching, so digital elevation models reaching from 1936 till present. So we really know the evolution of the glacier of what we might call some stage after the Little Ice Age until present. So very good set of data. Even some data being acquired for the hydroconductivities on the bedrock with certain speculation on what is actually there. But we know that the structure is, at least in the lower parts, cold ice above temperate ice and some frozen talus. This is a little bit of a speculation, and permafrost underneath. You've seen that picture before. So in this case, we are doing the ice flow modeling, Stokes, thermomechanically coupled, GLADS, and we are introducing 2 layers, mimicking a, if not frozen, a higher conductive sediment layer of about 3 meters, which is of course an assumption. It can be, I think, from 1 meter to up to 13 meters. So one can make variations in that. And then in this case, a bedrock to 100 meters I now came across the fact that actually we need a little bit more to completely capture the permafrost layer that is existing after 1936, where we start actually our investigation. So at the moment, the new model setup, which I will show in EGU in 1 week, will have already 500 meters of bedrock underneath. But let's stick to what we have here. So what we are doing is, this shows the glacier outline as it is in 1936. With the faint white line here, the glacier outline of the year of interest in the end, which is 1997, just as a reference how much the glacier has been retreating. And what we are doing is we are using the thermomechanically coupled ice sheet model above. In this case, actually with a temperature solver. The new version will be with an enthalpy solver, including a firn layer accounted for. We assume a fixed bedrock water pressure of 100% ice overburden at the bottom, and then a certain temperature distribution that should mimic the situation, the average situation at the 1936 time slot, so to say. Newer versions then actually really use climate data. We'll show that in EGU, and then run the whole thing and drive the groundwater permafrost model with all these inputs. And what we then get is a initial steady state situation of the permafrost distribution underneath the glacier. And one sees nicely the earlier in this slide showed wedge of frozen. So this is the white color here. This is he is the unfrozen water content. So if it's going to zero, it's basically full permafrost. If it's blue, dark blue one, it means that it's completely thawed, so the water can move freely inside the bedrock. And the groundwater flux in here, meters per year on the left-hand side. So this is our initial condition, and then we just take the distribution of the permafrost as it was in 1936 and now place the glacier or apply a glacier geometry of 1997 and run a whole yearly cycle of forcing on it to get an initial condition for the melt season of 1997. Okay, so this is the groundwater system. You see it's getting active in summer and then passive in winter, at least in this small layer. And this will act as our initial condition for the final simulation we are interested in, which is now a coupled simulation of the ice flow temperature distribution. Here on the right-hand side, we see glads. Those cones are the moulins, and the length of the cones is in proportion to the water that is being added at this very point in time. We start at day 161, which is the first melt day, and it goes until the end of the season where things start to freeze over again. Here we see the distribution on the right-hand side of the water pressure that is induced by this water being added by these moulins. And on the left-hand side, we see the reaction of the groundwater to the imposed water pressure from glads. And one can nicely see that the sediment layer is active in summer, and in winter it gets passive again, which is interesting because at the end of the season, we basically confine the system such that we press all the water into the still unfrozen forefield, and we get a lot of activity of upwelling flux, which is indicated here by these yellowish colors, which can be also seen in reality. I'll show you a picture in a second, but spot the high activity just before everything freezes over. Here's a freeze frame of this situation. So this is at the very end of the melt season, so to say, of the summer season. And we have this huge activity here in the front, in the forefield of the glacier, where else the subglacial system starts to freeze over already, shown here on the left-hand side. And taking a picture here by Dave Rippin, one can see these ponds of water in front of the glacier. Some of them actually are thought to be springs that really connect to this to the aquifer below, which we cannot simulate here because our permafrost thickness is still too thick. We would need also some more of geological information because usually those springs are along the lines of some faults or whatever, which of course are not accounted here, where we have a higher conductivity, where then also the permafrost can vanish much faster than it would in a homogeneous material. So geological information is very important for that. Talking of that spring, actually, Jack Kohler gave me the coordinates, which they think is a connection to the subglacial aquifer. So maybe we can, in a further simulation, include some weak layer in between that we can connect and see what would be the outputs in terms of volume fluxes from an aquifer below for such a spring. That's it, basically. So the conclusions, this phase of Cryosphere actually was for developing the tools that we then further need for investigating our sites, or in case of the gloves, then for a large-scale investigation of risk assessment in terms of gloves being potentially created. But we have mutually coupled thermomechanical ice flow running Stokes model, combined with subglacial hydrological model and a permafrost groundwater model, or geothermal groundwater model, so to say, implemented in the finite element code Elma Ice, and we can run it, and we are able to study the complete transient hydrological and thermal system from the glacier down to the sub-permafrost aquifer. We are able to reproduce seasonal outflows as we have seen now for Midre Lovenbräin. We will now turn to the sites that have been selected for CryoSCOPE to apply it there. And for the GLADS output trained with the machine learning model, we have provided Elma Ice output data to train as Nicola correctly pointed out, a hydrological model that then will be added to another trained glacier model, in this case IGM, to do potential analysis of cloth hazards in the future to come. That's all from my side. Thank you very much for your time and your attention.
Thanks a lot, Thomas, for this very nice presentation. We now have quite a bit of time for questions. There's a question on chat from Noeli. I think this is regarding Svalbard. So have you analyzed this water, and is it melted water from the glacier or groundwater arising to the surface?
I'm not a field glaciologist, so I for sure haven't done. I'm not aware of literature that for Midre Lovenbräin does this analysis, but definitely for Scott Turner Brain, there will be a chemical analysis and there will be investigation where exactly the water is coming from. That is a core part of CryoSCOPE, project, to have chemical analysis of water and then taking it to the sources where it comes from. So we will be, at least on Scott Turner Brain, be able to tell where the water is coming from.
Yeah, and just to add to that, I already heard from Andy Hodson, who is leading the work in Scott Turner Brain, that they already found a tracer which could help them disentangle between groundwater and glacier melt outflow. He would present this at some point during this year, but this is something we will try to investigate in the project.
Yeah, so thanks for that question. Very good question that directly linked to our plans.
Yeah. There's another question from Daniel Binder. Any idea of the age of the upwelling water? or the groundwater traveling time? So I guess transit time of groundwater.
No, to be honest, but should be possible to get because we know the flow rates. So yeah, good point, Daniel. One should look at that. Yeah. But I
And
haven't done this investigation yet.
And just a feedback for the audience, you can also raise your hands if you would like to speak up, and we will unmute you so that you can speak up. Next question is from Jessica. Are you able to apply the coupled model to selections of an ice field, that is, basins on glacier lateral margins where there is significant melt rather than glacier terminus?
I'm afraid I not completely understand the question. So, is it a terrain mixed between glaciation and non-glaciated, or?
Or maybe I can also request Mariam if you can unmute Jessica, and that way it's easier.
Yeah, hey, thanks for the presentation. Can you hear me now?
Yes, we can.
Yeah, so I'm just looking at if this model can be applied to kind of particular areas. So I'm thinking in context of the Juneau ice field in Alaska, how there's lots of different output glaciers contributing to the melt. And if you could apply this model to just look at a specific area, say like a basin that's contained by inuntax or kind of mountains and mixed terrain, rather than just glaciers that are terminating, either land terminating or land.
Yes, thanks for explaining. Very good question. I think you can, but of course the input data has to be consistent and good. But we have applied that model without permafrost naturally to an aquifer underneath the Maltesian Islands. Actually, there is a paper on that. So the area can be quite large. It can include also oceans, because the question there was the salinification of a freshwater aquifer underneath the island. And as you might have seen, maybe I can go back, but this is quite a long stretch here. No, not really. In the 97 configuration, the glacier ends here. So you have a vast forefield that is basically unglaciated, and there is nothing that prohibits you to extend that area further outwards. So in principle, I think you could. It is, though, a quite intensive computation. You have to be aware of that.
Daniel has a question.
Just have a question about like the Mittel-Löwenbräu. There you said you assume a fixed water pressure of 100% of the ice overburden. So that's quite an extreme assumption. So what are the reasons?
Well, that is just, I mean, I wanted to have some kind of spin up. Frankly, actually, it doesn't really matter, to be honest. I could just have skipped that part. But in the later case, I didn't, because this is really then using GLADs to produce the surface pressure.
Okay.
But this was just for getting some spin up of the system, that there is water flow, and then starting the melt season with something that doesn't have zero water flow and then would have bias in some way. So this was just for getting, how should I say it?
The system running, or
the system running, exactly.
Yeah.
Thanks for helping me out.
Okay, but like it's not like that. It's like constantly it is 100%.
No,
Like,
sorry if I didn't express this. So this simulation, so the real full capsule simulation, throws the water into the molars, and then the water is taken up by the GLADs, and GLADs produces a water pressure that generally will not be in equilibrium with the ice overburden, and then drives the flow. And you see that it's the flow is much more variable here. even underneath the glacier than it was in the previous simulation.
We have a question from Thomas. Thanks, Daniel, for your question. Thomas, you're on stage now.
Yeah, thanks for a nice presentation. I have a bit more detailed technical question. Since we have been doing related simulations in a very nearby area, a bit further into the same fjord. And that regards simulations using GLADS. And well, you have been showing here multi-year simulations that include extended periods of basically no surface water input. So how do you keep control of that GLADS actually conserves mass? We have, in similar simulations, we have experienced problems with where is no surface water input, then GLADS still will produce some kind of water flow, which at the end is unphysical once the reservoir is depleted. So how can you inhibit that?
Yeah, very good question. There is an issue with GLADS. You brought it to the point. If you deplete the system of water, it will create negative pressures that are unphysical. You can put in some thresholds, which is also, of course, cheating and telling that, okay, don't go below. But in the end, to get completely rid of that problem, one would need a modified version, which I think if I recall, in a conversation with Christian Schuf, he already suggested that there is a paper I think by him and Ian Hewitt on how to repair that issue. But yeah, it's a known issue of GLADS when you have when you choke the system from water, that it produces it can produce unphysical flow, and you cannot guarantee the conservation of water therein. Question is, do you need it inevitably for getting the interaction with the permafrost, or can you just skip those times where you basically have no water in the system at all and just move forward just thermodynamically with the groundwater system? Additionally, and I didn't mention that, and I have to be honest about that, also the groundwater system assumes that you have a saturated aquifer. So we cannot deal with Richard's equation that we can basically take out water from the bedrock so that the bedrock would be dry. That's also one constraint of the whole system. So yes, well, it's not perfect. Yes, but
in our simulations, this situation occurred many times, and so that's why we gave up at some point. But I think it's also this is not a natural situation, because all observations suggest that actually the system does not deplete, but it closes down and keeps the water stored inside the glacier. So if we look at the multi-year records of subglacial water pressures, they actually they increase during winter rather than decrease, what the model would suggest. So this means that the water is kept in the system, but we still have not figured out a way how to treat that with GLADS.
Okay, yeah, maybe we can take this offline. It would be interesting to exchange. I understand that anyhow we are in sister projects, right? Between CryoSCOPE, you are in help me out, which was
liquid ice.
Liquid ice it was, yes.
Yeah.
So I think this would be a good way to exchange. Maybe I got away with Midre Lovenbrain as an easier case and not the whole area. So that could be a reason for it. I don't know. The fact is that Lovenbrain doesn't really, as you can see on the simulation now, produce a lot of channels. So they shortly occur, but then quickly fade out. So you're not draining that much water out of the system. So maybe this is an answer that we don't have in such a severe way this issue. Plus, the simulation with glads I show you is just during the melt season. So we always have water there, basically. Maybe if I would continue into the winter where there is no water at all, I would get into exactly the same problem as you have.
Yeah, I would be glad to discuss that with you.
Yes.
Yeah.
Are you in EGU?
No, unfortunately not.
Oh, pity. Yeah. Okay. Yeah. Okay.
Well, we'll find a way. Thanks.
Yeah. Thanks for the question.
Thanks, Thomas, for the question, and Thomas for the answer. Are there any more questions from the audience? I don't see any more on chat. If you still have questions, you can raise your hand. We still have a few minutes. And maybe I had a quick question, Thomas, for you, which is not the work that you are leading, but what Nikolai is leading. So when you do an emulator or or more accurately, a machine learning model as an alternate for this, what is the gain in terms of computational time, and what is the loss in terms of physical information that we are talking about?
I think the first answer will be given when we have run the stuff. What one would then really have to do is make a full study of one glacier. First off, you always have to think of a machine learning model as kind of a statistical approach. So it is not 100% replacement of a deterministic model. Okay, so you're not comparing the same things here. Yet, having said that, to get a solution, say, for a certain glacier, one should compare simply to do the similar run with the process model and the inference of the machine learning model. I'm pretty sure the machine learning inference is infinitely faster than the process model. But you also have to account for the training of it. So that's usually what people forget. And that is the heavy lifting. And maybe Nicola already has some numbers at hand, what we are burning. I think I had to top up the CPU times and then later also the GPU time on Lumi already for this project. So it is not a free lunch to create a machine learning model out of a deterministic model. But maybe Nicola, are you here? Do you have some ideas or write in the chat? I see the chat flaring up, but I can't read it.
On chat, and unfortunately not yet, but soon. But Nicola is also here. He can add.
Yes, in terms of the training, can you hear me?
Yes.
Yeah, we're halfway done with the training data generation, and currently I'm in the process of actually preparing the data and selecting the chunks of data that will be used for the training. So it's not only the actual training that takes a lot of time, but also the pre-processing of the data. So data is huge as well. So in terms of the numbers, I unfortunately can't give any because we haven't done any iterations of the emulator yet, of the emulator training yet. But what I can say is that at least the architecture that we plan to use is obviously not only much faster than any sort of numerical model, but also because it's a neural operator, it's supposed to be, for a neural operator in this case, it's supposed to be faster than also like your typical neural network too. So that's as much as I can say at this moment.
Thanks, Nicola, for your input. Just to conclude, now I would also like to advertise a bit our upcoming session at EGU next week. So together with our sister projects IceLink and Liquid Ice, we are organizing a session at EGU. There will be two parts to the session, an oral block, which is scheduled on Thursday, 7th of May from 2 to 3:45 p.m. CEST in room 134 on the green floor. And the poster session would be on Tuesday, both the morning and the afternoon slots. I put a link to the session on chat. So if you're interested, I'm looking forward to seeing many of you there. And our next monthly webinar will feature work from Miko Stralendorf and is scheduled on the 20th of May. at 10 a.m. CEST. These monthly webinars would be organized every month, and we will put up an invitation to our calendar on our website soon. The upcoming presentation will summarize ongoing work on machine learning-based emulators for seasonal streamflow forecasting for Iceland. And with that, we will conclude our first webinar. Thanks a lot, Thomas, for presenting and for being really patient with the questions and answers. And thanks a lot, Maria, for organizing this. And thank you, everyone, for attending this and making this a very dynamic exchange. Hopefully, we'll see some of us would be there at EGU, and we'll see each other there. With that, I would like to thank everyone for their participation. And thanks again, Thomas, for the wonderful presentation.